Welcome to my channel. Another day, something to learn. What is the difference between classical computers and quantum computers? By classical computers we mean regular computers. We need to understand how classical computers work in order to understand how quantum computers work. Classical computers only know of ones and zeros. Whatever we write in a programming language, or open an image file or video file on our computer, the computer actually sees that kind of information only as ones and zeros. Why do classical computers only know ones and zeros? There are transistors in processors that can detect whether we have a voltage or not. Let's say when there is 5 volts it represents a 1, and when there is 0 volts, it represents a 0. If we can understand whether there is 5 volts or not, we can do a lot with this information. For example, when we write Python code, the computer eventually understands it as ones and zeros in machine language. As a result, computers only see ones and zeros whether we write complicated programs or plain English. That is all a computer can do. The revolutionary idea was that if we can store ones and zeros in a transistor or processor, then we can do anything. We can represent ones and zeros in a binary form. Consider the number 215 that we need to convert into binary. How do we do it? 215 is in decimal and we have 10 numbers, 0 to 9, whilst in binary we have only 2 numbers, 0 and 1. 215 equals 510 to the power of 0 plus 110 to the power of 1 plus 2 asterisk 10 to the power of 2. Converting decimal numbers into binary requires using the division by 2 method. Here's how to convert 215 into binary. Divide 215 by 2, and write down the quotient and remainder. 215 halves equals 107 with remainder of 1. Divide the quotient of the previous step by 2 and write down the new quotient and remainder. 107 halves equals 53 with remainder of 1. Repeat this process of dividing by 2 and writing down the quotient and remainder until you get a quotient of 0. The remainder at each step will be either a 1 or a 0, which will form the binary number. The binary equivalent of 215 is 11,010,111. Starting from the bottom, the rightmost digit, the remainders are read from the last to the first to form the binary number. If we can represent numbers in binary, it means we can represent our daily life numbers in binary, which means representing our daily life numbers in voltages 0 and 5. Consider the following hexadecimal number: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 A, B, C, D, E, F, where A, B, C, D, E and F represent 10, 11, 12, 13, 14 and 15 respectively. A4F6 equals 10 asterisk 16 to the power of 3 plus 4 16 squared plus 15 asterisk 16 to the power of 1 plus 6 asterisk 16 to the power of 0. Equals 40,960 plus 1024 plus 240 plus 6. Therefore, A4F6 equals 42,230 in decimal. Now we know that we can represent numbers whether they are too big or not, in binary. We do the same with letters, then tell the computer that if you see a certain number in a letter or alphabetical context, then do not convert this into binary or decimal. Just convert this into an ASCII form. We therefore can assign the alphabet to binary representation. The binary representation of the alphabet involves mapping each character to a unique sequence of zeros and ones. This can be done using the ASCII, American Standard Code for Information Interchange, table, which assigns a binary code to each character. The table consists of 128 characters and assigns a unique binary representation to each one. Binary is a numerical system that uses only two digits, 0 and 1, to represent all numbers and characters. Each binary sequence represents a specific character, and the same sequence will always represent that same character, regardless of context or language. As long as we assign something, for instance assign an emoji a decimal number, or binary number, the computer will know what it is dealing with. Now that we can represent letters in the form of voltage, we can combine all the 1 and 0s together to create a letter or an emoji. Creating a video, an image or sound uses the same logic. However, the difference is in the context. As long as we can tell the computer that it is in the context of an image, we can easily represent an image. Scientists came up with an idea that they can create any color with a coding system like RGB, or red, green, blue. If we combine red, blue and green in a way that is starting from 0 all the way to 255, we can have all the colors in a palette. This RGB palette can be converted into binary form as well, so that we can represent any color with binary. If we can create any color, we can combine or multiply all these pixels, which are the smallest part we can see on the screen, creating different colors in different areas of the screen. This way we can create images. Videos are sequential images, arranged one by one in a video. Hence we can create a video using 1s and 0s. The idea started with the fact that we can store 1s and 0s in a transistor. 1 bit equals 0, or 18 bits equals 1 byte. 1, 1, 1, 1, 1, 1, 1, 1, 8 bits equals 256 in decimal, meaning we can represent any number between 0 and 256 in one shot. In quantum computers, due to the fact that we can have some quantum properties like entanglement, same quantum state, and superposition, we can represent all the numbers starting from 0 to 256 at the same time simultaneously. Rather than only one number between 0 and 256, we can represent all the numbers simultaneously. The calculation possibility has been increased in an enormous way. Quantum computing can change our lives in a substantial way if we can leverage its potential. Thanks for watching, and don't forget to hit the like and subscribe buttons.